Hello everyone. Today I'm going to be talking about how to get geological information out of geophysical datasets, in particular using machine learning and 3D mapping techniques. So exploration today involves collecting a lot of detailed geophysical data like magnetic data, radiometrics, gravity. And these surveys are typically pretty expensive to run. And the point we want to make here is, because they're so expensive, we really want to make the most of them. And in particular, we want to try and extract as much geological information from them as possible. We're going to show that we can use modern techniques like machine learning algorithms and 3D mapping to extract this geological information and produce useful geological models that can be used to make exploration targeting more effective. And we're going to do that through a case study of the Fletchers Awl copper gold project in Central Queensland, which Connects are exploring in partnership with Longreach Mineral Exploration. Longreach are a fairly new exploration company exploring for copper gold in Australia, and they're using their advanced knowledge of geophysics gained from years of oil and gas exploration. And Connects are helping them in terms of their mineral potential mapping and in terms of this geology mapping work. Here's the project. It's located in Central Queensland, northeast of Claremont, and it was identified as being prospective for epithermal and porphyry mineralization during Connects' mineral potential mapping. The geology of the area is largely covered by thin tertiary volcanics, but in the area where Longreach are exploring, there's a small basement inlier. So there's a core of granite, which is surrounded by sediments and volcanics of the Bowen and Drummond basins. There's also a very small outcrop of diorite. And there are a whole host of small old workings scattered throughout the andesitic volcanic units around the core of granite. These are variably described as porphyry or epithermal copper, gold, or silver deposits. So initially we kind of expected that the source for these deposits was likely the big granite in the center of the basement inlier. However, once we looked into it, this granite was seen to be an S-type granite, had the wrong age, so it's clearly not the source. So we want to understand the geology better to try to understand what is the source for the metals, what's the source for the fluids, to help effective targeting in the future. In 2021, Longreach decided to fly a high-resolution magnetic radiometric survey to get a better idea of the geology. You can see on the bottom right that the pre-existing data was not particularly helpful. It was flown, I think, at a 200-meter flight line spacing, so it wasn't very easy to see the geometry of the units. Whereas on the top there, you can see the new data is very nice, and you can really see the shapes of the units. You can see narrow veins, you can see structures that are going to be critical to understanding the mineral system. So we wanted to use this new detailed geophysical data to produce a nice 2D solid geology map that shows the units relevant to the porphyry or epithermal mineral system. So we want to strip away that tertiary volcanic stuff and give us a view into the basement rocks. We decided to trial using machine learning algorithms as a way of improving the speed of the process, but also to make it more objective. So instead of having a human decide where the boundaries go, we're going to let the machine decide. We tried two different methods, random forest and support vector machines. I won't go into details of how these work, but essentially they consider all of the input maps at once in a multi-dimensional space, and they look for relationships between all these maps and the training data that are fed into the algorithms. So where they are a big improvement on humans is that they're able to look at 10, 20, 100, 1,000 maps at once, rather than considering the relationships of each map individually. So here's a typical workflow that Connects uses for our machine learning geology mapping. So the first step is always to define the training data and the input maps. Training data are just points where we know what the geology is, and we use that to train the model to give it some guidance. So in this case, we want to know points on the surface where we know what the geology is. So we use sampling sites, observation sites, and drill hole logs. So we're fairly confident in what the geology is at these areas. In terms of input maps, we used all of the newly collected magnetic and radiometric maps, a variety of derivative products like vertical derivatives and things. We included a DEM because certain units might have certain topographic expressions. We also put in a bunch of ASTA maps. So basically we start off with any geophysical maps that we think might be useful in terms of the geology, and then during the modeling process we'll refine these and take out any maps that don't work. Second step, train the model. So we feed the model the training data and all the input maps, and we let it look for relationships between the training data and the maps. So it's trying to figure out, what's the signature for the granite, what's the signature for the sandstone, and then it basically comes up with equations to relate these two things together. Third step is then to use these relationships to classify the original raster to produce the geology map. So it uses the relationships and it looks at each pixel and it decides what's the nearest classification that would satisfy the relationships. Then we look at this geology map and we validate it. We say, is this geologically reasonable? Does it match the geology we know about? So if we've got areas that are well mapped, is this reproducing those well mapped areas? And would it make sense in 3D? Can you draw a cross section through this map and it still makes sense? If not, we go back to the start. We go to step 1. We maybe alter the training data. We have a look at it. Maybe some of those points are a bit dodgy. We're not totally sure about what the geology is on that point. We might delete that point. We might add in more to give more constraints for certain units. We might change input maps. So there might be a map that's really dominating the output, or a map that's just kind of a bit too messy and it's not helping. So we might remove that. We might add other maps in if we have other ideas. We can also alter the modeling parameters to try to really hone in on a good result. So we ran 29 different models, varying, as I said, the training data, the input maps, and the modeling parameters. And here's just an example of 4 maps, starting from the left with the first iteration, going to the right with the final map. So these are all random forest maps. So you can see on the left that first map is very noisy. It doesn't really look like geology. It kind of looks like a messy version of the geophysics. But then as we go back and we improve the training data and we change the input maps, the map improves, and by the end on the right there, we've got a map that's looking quite reasonable, quite like what we know the geology, where we know the geology well. It's reproducing it, so we're pretty happy. These are the final maps compared to the existing geological survey map on the left. So you can see in areas where the basement is outcropping, so the purple, reds and blues, the machine learning maps are doing a pretty good job of matching it. So we're quite happy with that, and we're confident in the relationships that it's found. But where these techniques really come into their own is that they're able to apply these relationships undercover. So especially in that area to the southeast, you can see that the machine learning tools have mapped out a big diorite intrusion. So that can have potentially quite big implications when you're exploring for porphyry and epithermal mineralization. So we're happy with these maps. They've done a good job at reproducing the known geology. But to add extra detail, we gave these to Peter Kovac, who then did a manual interpretation of the magnetic and radiometric data using these machine learning maps as a guide. This nice 2D geology map, we want to extend it into 3D. We did this in Micromine, creating a workspace that includes a 2D geology map, a 3D inversion of the magnetic data, and other datasets such as drill hole logs. This allows us to visualize all these different datasets in 3 dimensions and try to get an understanding of what the geology is doing in 3D. We start off by producing strings for each wireframe. These are lines that are digitized manually. So essentially we consider all the data, we use our geological knowledge, and we draw lines that represent the boundaries of each geological unit. We then let the software tools join the lines together to produce a solid wireframe. Then use Boolean tools to cut these wireframes to avoid any gaps or overlaps between the different units. And this produces a final solid geology model which makes geological sense and follows the rules of superposition. We use a macro to record this process so that in the future, if new data are collected or if the geological interpretation evolves, we can go back and we can make changes and update the model easily. Here are the results of the 3D geology mapping. We managed to model all of the units and structures which were identified in the 2D map and extend them into 3 dimensions. Essentially, the model shows a central laccolith of S-type granite which is draped over by volcanics and sedimentary units. But the most interesting thing out of this model is the presence of these buried I-type intrusions which correlate with the small diorite which is seen at surface. And the 3D modeling shows that these intrusions are a lot more extensive at depth than they would appear from the surface. So it's potential that these are quite important for this epithermal porphyry mineral system, and they could represent the source of metals and fluids for the mineral system. And having the 3D geology map allows us to identify specific prospective zones where we can tell the client to go and target with their drilling or their sampling in the future. In this case, structures that intersect these prospective intrusions should be focused on. So here we've shown that using these techniques, machine learning and 3D mapping, allows a lot of geological information to be extracted from the geophysical datasets. In this case with the Fletchers Awl project, it really improved the mineral system model, so it helped us understand where the fluids and the metals were coming from. More importantly, it highlighted these several prospective zones which could be targeted in the future via sampling or drilling. And understanding where these are in 3D is particularly useful for drill planning, so you'll be able to plan your drill hole to go straight into the target. And these geology maps, these products, the 2D and the 3D geology maps, can be updated easily to incorporate the most up-to-date knowledge. So if the understanding of the geology or the mineral system evolves, we can incorporate that, or if new data are collected, if someone goes out and does some more mapping, we can use that to update the model, which allows more effective exploration. Thank you.